going to finish them all today. And so they're going to end up hanging over a little bit. And because there's like boxes to fill in, I think it might be easiest if I start by writing up here, and then when we start to solve problems, I can move to the smartboard to do that. So, all right, I'm going to back up a little bit. We kind of touched on this the other day, but we are going to be talking about linear and angular momentum. So the word momentum is one of our conservation laws. It's one of the 4 things that's always conserved. So I want you to mentally know that linear momentum is always conserved. Linear momentum is what we learned last year. Whoops, I'm doing the wrong thing here. So I'm jumping down here. Momentum, P equals mv. And angular momentum is always conserved. And this is the one time we switch variables. So the variable for angular momentum is an L. But I hope you've picked up by now, it's not just mass that's important to us. It's the distribution of mass, which is hidden in an I equation. And then our V's become W's. All right, there's 2 kinds of momentum. Both are always conserved. All right, popping up to the top. Impulse. An impulse causes a change in momentum. So impulse is J, and that is Ft. And we talked about this last year, so I'm not going to repeat it, but I gave you an example so you'd have one in your notes. It says airbags increase the time of a crash, thereby reducing the force of impact. So if you increase the T, you can decrease the force that acts on the person. This is the crash. Okay, the crash can be the same, but you can affect the force by increasing the time. All right, so over here, we also have impulse. But instead of force, we're going to have torques and still time. So I'm just going to call it a TT. You need to always remember that when you write down torque, you can always replace a torque with an F and an R. And same thing, I wanted to give you an example. It says increasing the time you apply a force to a merry-go-round allows you to create a smaller torque. So let's say that my job is all these people are on the merry-go-round, and my job is to spin the merry-go-round. So I could walk up to the merry-go-round and like apply a really big torque. A torque is an F, my force, times an R to the outside of it. So I could go like this really hard to try to get them to whirl around. That'd be hard for me to do that. So instead, I might decide to run around the merry-go-round as I'm pulling. And so when I do that, I'm increasing the time, which would allow me to get a nice rotation, but by applying a smaller torque. And when I say small, by applying a smaller torque, that implies 2 things. I could apply a smaller force, that's really what I was hoping to do, but I also could then put my hand in a less effective place. Like it's most effective to have a big R, like to put my hand on the outside of the merry-go-round. But now I could put my hand in the middle and maybe that would help. So increasing time, I could put my hand someplace else. In real life, putting your hand on the outside is going to be the easiest thing to do anyways. Okay, but what I really wanted to look at here, since I think you kind of get the concept of impulse, is I want to look at the units. I don't have these units memorized. I figured them out. So force is in newtons, and time is in seconds. I'm going to break a Newton down. A Newton is a kilogram meter per second squared. How did I get that? From F equals ma. And this is a second. And so this second would cancel with this squared. So I'm going to go cancel, cancel. And I end up with kilogram meter per seconds. Kilogram meter per seconds. What about on this side? A torque is an FR. That's going to be a Newton meter. And then I have this second. I'm going to break the Newton down into a kilogram meter per second squared. That's F equals ma. And then I still have this meter. I'm going to put that there. I still have that second. I'm going to put that there. And this second can cancel with this squared. And so on this side, I end up with a kilogram meter squared per second. Kilogram meter squared per second. So the units are different for linear momentum and angular momentum, or for linear impulse and angular impulse. And just be able to figure them out. And why I point that out is on our AP test, we always want to put down units. They don't take away points for bad units, but they often give points for good units. So we always want to guess our units. All right, now let's go up here to momentum. And we'll do the same thing. Let's play with the units. So momentum is going to be mass times velocity. So that's going to be kilograms. And velocity is meters per second. So those are going to be the units for momentum. And notice they match. These two units match because impulse and momentum can be set equal to each other. All right, let's look over here. An I equation is always some sort of mr squared. So here's m. Here's r squared. R squared. And W, omega, is radians per second. But a radian is a nothing, so I'm not going to write it. So I have a rate, well, you know what, I'll cross it out when I do this. Radian, a nothing per second. And so you see I have kilogram meter squared per second, which matches this. So it's the units that we have to pay attention to there. All right, and then the last thing that we'll write down is the impulse momentum theorem when we hook them together. Impulse will create a change in momentum. Impulse will create a change in momentum. So let's break that down one more time. Momentum is an mv. mv. Well, mass never changes. So the change can't go with the m. The change has to go with the v. So if you apply a force for a period of time, you will change the velocity of something. And over here, we have impulse, tt. tt will create a change in angular momentum. Whoops, that's not a change. Delta. And the change can't go with the I because you're not changing the I equation. So it has to go with the W. So you'll change the rate of rotation if you apply a torque for a period of time. Okay, so this problem number 1 example, it should be pretty short and sweet, but let's work through it quickly. All right, it says, I'm going to draw a picture as I draw. All right, that's a merry-go-round. A force of 125 newtons, so I'll do this. So if somebody is applying a force of 125 newtons, is applied to the edge of a 100 kilogram merry-go-round that has a radius r of 2.5 meters for a time of 5 seconds. So again, they're kind of like running around for 5 seconds. So time is 5 seconds. All right, find the impulse produced. Impulse is J. And that's torque times time. And the torque that I applied, when you apply a torque, the F has to be perpendicular to the R. Well, with what I did, that makes it nice and easy because it is perpendicular. So FR times the time. So 125 times 2.5. And I did it for 5 seconds. So I'm sure that works out just great. And look how I left my units. Newton meters per second. Because torque, well, there's newtons, there's meters, and then there's seconds. So you can write it that way. You don't have to break it down. All right, what is the angular momentum of the merry-go-round? Well, impulse equals momentum. That's the impulse momentum theorem. So if you know the impulse, you know the angular momentum. So that's why it's the same answer, and I don't have to do anything. All right, what is the resulting angular velocity? Well, that's when I want to kind of break it down. So I know that this answer is 15. Yeah, got to move it up. Sounds good, thank you. So I have my impulse, and that's going to end up equaling the IW. And what I'm solving for is the resulting angular velocity. All I got to do is figure out what I is. So I'm going to switch colors here. So I'm going to have 1562.2. And a merry-go-round is a disc. So that's a 1/2 m. Someplace they told me the mass, 100 m r squared. 1/2 m r squared W. And then I'm solving for W. And I'm assuming that answer works out, and we would know that the units would end up being in radians per second. So again, it always helps me to try to take the words and turn it into like a real life picture. I want to just point out one thing that could be complicating. What if this person applied a force at an angle, like they did this? Like pulled it out like that. Remember that you have to use the F that's perpendicular to the radius. Okay. All right, we're going to flip it over. And I am not going to do the calculus part of this today. I'm going to save that part. All right, so we're going to start with how to derive Newton's second law. Newton wrote his second law, F equals ma, in terms of momentum. He didn't write it F equals ma the way you and I learned it. He wrote the impulse momentum theorem. So I'm going to write down Ft. Oh, I'm sorry. This is last year's stuff. This is the angular column. This is last year. This is this year. All right. So Ft equals mass, change in velocity. That's how Newton wrote his second law. So picture all the time that we write down F equals ma. we would have to start with this. And then the next step is to divide both sides by t. But when I divide both sides by t, I'm going to put the t only under the v. So it looks like that. And then you talk to yourself and say, oh, well, a change in velocity over time means that I must be accelerating. And that's the way we learned Newton's second law. But technically, there's 2 steps before it. Except every step would start with this, would go to this, and then would turn out to be F equals ma. So we just learned it F equals ma and then kept on going. But we should respect that F equals ma came from the impulse momentum theorem. And we can do the same thing over here. So now we talk about something that's rotating like a merry-go-round. So I have torque in time equals the rotational inertia and a resulting change in velocity. Divide both sides by t. And if the speed at which something is rotating is changing, it must be accelerating, t equals I alpha. So same sort of concept there. Okay, I want to just give you a tidbit taste of how calculus is going to come into play, but we're not going to do that part today. So if I did a graph, and on the x-axis I put time, and on the y-axis I put force, and I'm going to take an object and I'm going to apply a force of 10 over a period of time. So I'm going to apply a constant force. So it would look like that. What does the area under this curve stand for? How would you find the area under the curve? Length times width, F times t. F times t is impulse. So I'm going to write down area equals impulse. And equals, doesn't impulse equal momentum? So if someone gives me a force versus time graph, I now can find the area and I know the impulse, or I know the momentum. You know both of them. From a calculus standpoint, what if the force wasn't constant, but it was variable? How would you find the impulse or the momentum? You'd have to integrate that. Okay? And if you can see that you'd have to integrate that, then you know that if you took the derivative, you could be finding the opposite. So if someone gave you the force and you took the derivative, you could get the impulse or the momentum. All right. So we just have to expand that a little bit. So we'll save that for another day. Okay. We'll come back to this and we'll come back to this, and therefore we'll come back to this. All right. I'm moving on. So we are focusing now on angular momentum. And when someone says angular momentum, I would like this equation to jump in your head. So every object has momentum. Every object, everything we talked about last year had momentum. So if something's rotating, that's perfect. I just have to know the I equation for the shape, how fast it's rotating, and I know the angular momentum. But what if I had a moving particle? And the example that we often find is like a bullet. So I'm going to draw a bullet. Here's a bullet. probably in the wake of this week. That's not a good example. Okay. All right, we have a bullet. And you say, well, the bullet's not rotating. But I need it to be, kind of. So I'm going to take this equation, L equals IW, and I'm going to break it down. I'm going to derive another equation that I could use instead of IW because it's really not rotating. All right, so the I equation of a bullet. Oh, in the AP people, they like to fire bullets and they like to fire clay. They fire clay out of a gun. Why do they fire clay? Because then they can fire the clay and it sticks. They want it to stick to it. Okay, the same way last year we had a train car comes in, crashes into another train car, and they stuck together and they moved off together. So that's why we fire clay, because it will stick. We fire a bullet because it gets embedded in the block. We want it to stick together. All right, so a bullet then, or a piece of clay, is going to be a point mass, So I'm going to write down mr squared, because that's the equation for a point mass, mr squared. But if it's a bullet or a piece of clay that I'm firing it, it's moving with a velocity. So I'm going to look at that W, I'm going to look at that V, and how about we just use this equation? V equals RW. So what could we replace this W with? V over R, with me? V over R. And then this R on the bottom will cancel with this squared. And I will be left with MRV. So let me say that again. When we do angular momentum, if there is anything in the story that's rotating, you are forced into rotation. If there's anything in the story that's rotating, L equals IW. But there might be another piece in the story that's not rotating. Then you have to use the alternative form, L equals MRV. I'm going to write it here. L equals MRV. Last year, I don't know why, but last year, they named this MERV. I don't know really well. I mean, it kind of makes sense. MERV. And that helped them remember it. Okay. L equals IW and MERV. All right. So when someone says angular momentum, I'd like both of those equations to jump in your head. Okay. So moving to what we're going to do with all of this is the big topic is going to be conservation of momentum. We're going to review old momentums later. MV plus MV equals MV plus MV, blah, blah, blah. But right now, we're going to practice IW plus IW equals IW plus IW. And we know that both linear and angular momentum are always conserved. So I came up with 1, 2, 3, 4 situations that I keep seeing like over and over again. They change up the picture a little bit, but it goes something like this. There's one thing, maybe like an ice skater. And the momentum before is her arms are out, and then something happens and her arms are in. That's going to be conservation of angular momentum. If it's not an ice skater, what could it be? Oh, the AP people might make up an apparatus that has its arms out, and then you hit a button and it collapses. You say, oh, it's the ice skater thingy again. Or the reverse. The arms are down, the arms pop out. Okay, you got to recognize that as angular momentum. A second example. This is a record turntable. So I have a turntable going around, and I'm going to put a record on it. Record is going to drop onto the turntable. So I have two things, and they're going to come together. You got to recognize that that's angular momentum. The two things could come together top to bottom, or you could have two things spinning on an axle, and the two wheels come together and become one. This is a merry-go-round with a kid on a merry-go-round. All right, so pretend this is the merry-go-round. Right here. This is going to be the center of the merry-go-round. So I'm the only person riding the merry-go-round. I'm going to stand out here. All right, so one of you then makes me move. So here I go. All right, and now I'm going to change the location of myself. I'm going to take a step forward. What happens to the velocity of the merry-go-round? It starts spinning faster. Why does it spin faster? Because there's more mass towards the center. And so you realize that the merry-go-round going around and around, I can control the velocity of the merry-go-round by just where I step, where I put myself, okay? All the people move out, all the people move in, and so you have something that's rotating, and then AP language, oh, something comes and lands on it. What would that do? Then it moves to a new location. And so I call that like the merry-go-round example. And then the classic, I'll call it the rod or the meter stick. So we have this rod that maybe it's pivoting about its center. Like this, has the ability to pivot about its center. It's like this. And then I'm going to shoot the bullet into it, and it's going to cause it to rotate. The bullet's going to become embedded and cause it to rotate. Or I shoot the clay. Here comes the clay, shoot the clay, sticks, causes it to rotate. Or maybe it's pivoting about its end, and you shoot the clay someplace else. Or maybe it's pivoting here involving a parallel axis theorem, and you shoot the clay, okay? So, and it causes it to rotate. So I think if we could like kind of really understand conceptually these four examples, we can take most situations and kind of line them up with one of them to kind of help us think about it. All right, so this is an instance where the homework is not really homework. The homework are all of the example problems that you and I have to go through and talk about, so this makes some sense to us. So we are going to maybe do, I don't know, number 1 and maybe number 2 today. Let's see. So there should be room to solve these on the paper, but if you're a person who likes lots of space like me, you might want to do them on lined paper. Okay, number 1. I picked this one because it's a web-assigned question that never makes any sense. So here we go. A 6-kilogram particle moves to the right at 4 meters per second. What is the angular momentum about point P, about point O? All right, let me say that in casual language. Picture that particle as a bullet. So here we are, firing a bullet this way with a velocity of 4. And the bullet's just going to go straight. Just going to go straight. But then they say, what is the angular momentum about this point? And you say, well, angular momentum, it's not even rotating about that point. So that's why it seems confusing. But do you agree that it at least passes that point? It does. It does pass that point. So as it's passing that point, I'm going to draw in this. Like how far it is from that point. And I'm going to call that R. And since it's a bullet traveling in the straight line, I'm going to use the alternate version. I'm not going to use the L equals IW because it's not rotating. but I know that that's going to be equal to Merv. And so the mass of the particle is 6. I'm going to skip R for a minute. The velocity of the particle is 4. The R and the V have to be perpendicular to each other. So there's the V, and you can see that the R that I drew is perpendicular. So I can't plug in this 12. I need to know R. And so this is 30 degrees. So how could we get R? Sine. So sine of 30 will end up being R over 12. Is sine of 30 0.5? Yes, no? Sine of 30, is that 0.5? 0.5 times 12, 6. R equals 6. This is tough to recognize. This situation is angular momentum. So the more times we see it, the more apt we're going to be able to recognize it. All right, I'm going to read number 2, and I'm going to draw a picture as I do it. All right, a planet orbits a massive star. So here's the star, like the sun. A planet orbits a massive star at one location in its elliptical path. Do you remember in the elliptical path, the sun is not in the center, it's at one of the foci? So I'm going to go like this. Foci is focuses, I don't know. All right, so something like this. That is an egg. It's a good egg. All right, this is the planet. What is the distance between the star and the cloud? Oh, hold on. I got to think through it. What is the distance? That's far. Okay, so the planet's here. All right, at one location, it has a speed of 45,000, and it is this far from the center of the sun. So the radius is 1.25 times 10 to the 15 meters. What is the distance between the star and the planet? R, question mark, when it has a speed of 41,000. No, it's about the 18th spam message I got today. Jose is texting me again, the drug dealer. Okay, so you know what? You should recognize this from gravitation. What equation would you have used in gravitation? RV equals RV. Oh, listen. You're not allowed to use RV equals RV now. Because now you have to know where RV equals RV came from. And you have to say, oh, this is kind of like the merry-go-round where the object is changing its location. So I'm going to write down, oh, and by the way, it is rotating around the sun. So I'm going to write down the momentum before equals the momentum after. The IW before equals the IW after. What do you think the I of a planet should be? Did they tell you about the radius of the planet anywhere? No. That means that we, in the perspective of grand space, you can treat the planet as a point mass. So he's an mr squared. He's an mr squared. And W, we don't know his W, but we could do this. V equals RW. We could replace the W with a V over R equals. Over here, we have an mr squared VR. Did the mass of the planet change? No, so I'm going to cancel that. I can cancel this squared with the R on the bottom. I can cancel this squared with the R on the bottom. And look what's left. RV equals RV. RV equals RV. So, okay, so this is, I couldn't explain to you where this came from back in the gravitation unit because we really hadn't really focused too much on momentum. But I did show you this once. We're going to make a rule in our class. You can use RV equals RV anytime you want, unless it says, and on the AP test, unless it says derive from conservation of momentum. So this is derived from conservation of momentum. On the AP test, you can write down RV equals RV, but 9 times out of 10, they're going to put in the question derived from conservation of momentum. They're going to force you into the derivation before you get to the RV equals RV. Jack, question? That was my question. That was your question. Okay. All right. Let's stop there, and we'll pick up on Thursday.